All right, today we're jumping into the world of the absolute heavyweights of the periodic table. I mean, these are the elements that are quite literally the backbone of our modern world, structurally, colorfully, and industrially. We're talking about the transition elements, the titans of the periodic table.
So when I say the word metal, what's the first thing that pops into your head? For most of us, it's probably something like the iron in a bridge, maybe the copper in our wiring, or even gold and silver. These are the elements that pretty much define what we think of as a typical metal.
And you know, there's a really good reason for that. All these familiar metals, they all live in the same neighborhood, this big central block right in the middle of the periodic table. They're the real workhorses, the reliable elements that build our world, from skyscrapers to the very pots and pans in our kitchens.
But here's what makes their story so fascinating. It's all about who they live next to. Right over on their left, in Group 1, you find some of the most volatile and honestly just bizarre metals on the entire planet. We're talking about elements that will literally explode if you just drop them in water.
This huge difference kind of begs the question, right? What separates these steady, strong titans from their wildly reactive neighbors? What's their secret sauce that gives them all these unique and incredibly useful properties? Well, let's dive in and find out what makes these titans tick.
To really get a grip on the transition metals, we have to see them in contrast. This is really a story of two very, very different families of metals.
So on one side, you've got the alkali metals from Group 1. Think highly reactive, soft, and so light they can float on water. And on the other side, the transition metals. Hard, strong, dense, and way less reactive. The difference is just, it's night and day. All right, so let's get specific. How do these two families really stack up when you look at their physical properties?
The difference in strength is just astounding. You could take a regular knife and slice through a block of sodium or potassium like it was cold butter. Now, try doing that with a block of iron or copper. No way. Transition metals are hard, they're strong, they resist force, and that's exactly why we build bridges with them.
And that strength, it carries right over to their melting points. An alkali metal like potassium melts at just 63 degrees Celsius. A really hot summer day could almost do it. Meanwhile, iron won't even start to think about melting until it's over 1500 degrees Celsius. And that's all because the metallic bonds holding them together are incredibly strong.
But maybe the most crucial difference is their reactivity. You drop an alkali metal in water, you get a show, fizzing, fire, sometimes a real explosion. You drop a piece of copper in water, and, well, nothing happens. Crickets. This low reactivity is what lets us use them for things like water pipes, jewelry, and coins that can last for hundreds of years.
Okay, so beyond their physical toughness, transition metals have some unique chemical abilities that really set them apart. You can think of these as their chemical superpowers. First up is what I like to call the chameleon effect. See, Group 1 metals can only ever lose one electron to form a +1 ion. That's it. But transition metals are way more versatile. An iron atom can lose 2 electrons to become an iron 2 ion, or it can go ahead and lose 3 to become an iron 3 ion. So why can they do this? The secret's in their d orbital electrons, which are so close in energy that different numbers of them can jump into the action. It's this flexibility that's the key. And that ability, being able to change their charge, is the secret to their next superpower, creating this incredible world of vibrant color. While compounds made from alkali metals are almost always just plain old white crystals, transition metal compounds are famous for being colorful. It's all because those d orbital electrons can absorb and spit out light at different frequencies. We see this chemical rainbow all around us. That beautiful blue of copper sulfate solutions, that's from copper 2 ions. Iron 2 ions give you a pale green color, but iron 3 gives us that reddish-brown color of rust. You can even get these deep purples and bright oranges from compounds of manganese and chromium. It's just spectacular. This brings us to their final, and maybe their most important, superpower, catalysis. So a catalyst is basically a chemical matchmaker. It speeds up a reaction, helping it happen faster and with less energy. But it doesn't actually get consumed in the process. It just helps things along. And when it comes to catalysis, transition metals are the undisputed kings. They are the invisible hand behind countless industrial processes, making reactions possible that would otherwise be way too slow or expensive. We're talking over 90% of industrial chemical processes rely on them. Their impact is just staggering. Think about the food on your plate. The fertilizers that helped grow it were likely made using an iron catalyst in something called the Haber process. The margarine in your fridge?
made solid using a nickel catalyst. And every time you drive, platinum and rhodium in your car's catalytic converter are silently turning toxic fumes into safer gases. They are truly shaping our world from behind the scenes.
So after seeing all their unique properties, let's kind of pull it all together and really understand why these titans are so essential to everything.
So what really defines a transition metal? It pretty much comes down to this checklist. They're strong, dense, and hard with super high melting points. They've got that chameleon-like ability to form ions with different charges, which lets them create colorful compounds and act as incredible catalysts. And all of this is built on a foundation of being relatively low-key and unreactive.
You know, this quote really says it all perfectly. They truly are the functional backbone of chemistry. They give us strength for our buildings and machines, the vibrant colors for our paints and art, and the speed for the industrial processes that power our whole civilization.